Well, good day, everybody, and let us jump into another unit. In this unit, we're going to focus on solutions and an intro to equilibrium. So let's get started with this consider. Consider a solution composed of 2.5 grams of calcium chloride and 50 grams of water. Okay, I can imagine that, right? What is the solute and what is the solvent? Okay, I think we need to know something more about a solution. So let's go with some notes. Let's start off here with solutions. And as you all well know, I like to start off with a definition. So what's a definition of a solution? Well, here's one that I like. It is a uniform dispersal of one substance throughout another. Yes, so that means I have something dispersed uniformly throughout another substance. Good. Now we know this as, also known as, aka what's also known as a solution, a homogeneous mixture, right? That's what a solution is, a homogeneous mixture, meaning a mixture in which there is a uniform dispersal. Good. So this is our definition. I like this definition a lot, so that's the one I would use on a quiz. Now, let's talk about the components. Components which compose a solution. A solution is made up of two parts, something called the solute and something called the solvent. And the solute is the substance in a solution in lesser quantity. And in contrast, then, the solvent is the substance in a solution in greater quantity. Okay, good. That's pretty simple. And I think we can answer our first question. Consider a solution. Okay, so I'm considering a solution. So here's my solution. And that means I have uniform dispersal of one thing throughout another. What is my solute? Well, solute is lesser quantity. So I have 2.5 grams of calcium chloride. That means that I would have my calcium chloride uniformly distributed, right, throughout my solvent. And my solvent is what? My solvent is in greater quantity water. So I would have waters throughout this, and we would have a uniform dispersal. I should change some of these. So like this, yeah, right? And I would have then a uniform dispersal of my waters and, excuse me, of my chlorides and my calciums throughout my water. Good. Now, what is my solute again? It's the one in lesser quantity, calcium chloride. What is my solvent again? Water. It's the one in greater quantity. Cool. Easy. You guys do this one, bring me back. Solution composed of 25 grams of ethanol. What is ethanol? Ethanol is what? CCOH with some hydrogens around it, right? Something like that. That is my ethanol. Good, C2OH. And I have 15 grams of water. Which one of these is in lesser quantity? The water. So water is my solute. And what's my solvent? Yoink, ethanol. Are you saying that water doesn't always have to be a solvent? Yes, I am saying that water doesn't always have to be a solvent. It is usually a solvent with us, but it doesn't have to be. We go with the definition. Solute, lesser quantity, solvent, greater quantity. Cool. Moving on. Consider an aqueous solution of calcium chloride. I should use better English here, shouldn't I? Describe the process on a molecular scale. Is this an example of solvation or hydration? Ooh, this is starting to sound a little more complicated. And indeed it is. Let's go back to our notes. And let's come down here and let's talk about the process. What is the process of making a solution? And the process of making a solution is what we call solvation. This is the process in which a solution forms, or maybe by which a solution forms. That is called solvation. Okay, so let us think about, just as an example, let us think about sodium chloride, salt, as we know it, table salt, dissolving in water. Now, the first place I want to start is let's try to visualize this. What does sodium chloride look like? Well, first thing you'll remember is that this is a metal plus a nonmetal, so that means I have what? And if we're saying this is solid and this is liquid, then what do I have? Well, I have a lattice, right? A matrix. That means I would have sodium and sodium and sodium and sodium, right? And sodium, and I would have this lattice of sodiums, right? And they're all attracted to each other through Coulomb's forces of attractions, right? And here's my chlorides in between. The negatives are attracted to the positives, which are attracted to the negatives, which are attracted to the positives. And I would have something that looks like this, correct? It would be a lattice. Now, what does my water look like? Well, my water looks like this, and I need to have a couple colors, don't I? Well, let's go with the oxygens being, how about green? Okay, so here's my oxygens. Whoa, that might be hard to see. Yoink. Let's try blue. There we go. These are my oxygens, right? And here's another oxygen, and here's another oxygen. Kind of have this probably way too big. And then I have some hydrogens, right? And hydrogens. And I have unshared pairs, right? Remember, there are two unshared pairs of electrons on my hydrogen. And what do we have going on right here? And what do we have going on right here? We have what? This is hydrogen bonding, remember? Where I have an attraction between hydrogen bonded to oxygen and an unshared pair. So these waters are not just floating free, they are attracted to each other, and it's a relatively strong attraction because hydrogen bonding is relatively strong. So that's what the situation looks like before. So I would have this, my sodium chloride, being added to this, and then what do I get? When I'm done, what's going to happen? Well, I'm going to have a chloride, right? And what part of the water is going to be attracted to the chloride? Well, chloride is a negative, so that means my hydrogen side of my water is going to be attracted to my chlorides. And that would mean then I'll have my oxygen side like this, right? And I have my unshared pairs, yoink, 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 yoink. Looks like Mickey Mouse, doesn't it? Yoink, 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 yoink. Okay, these guys, different picture, right? But there is an attraction here because this is partial positive, this is partial negative, right? And there's an attraction here. So the partial positive side of my water is attracted to the chlorides, right? But then what's attracted to the partial negative side? Well, the partial negative side of my water is attracted to a sodium. And that sodium then would be surrounded by other waters. I don't know exactly how many, whether it's 3 or 4 or 8. But then what's going to be attracted to my, we got to put in some hydrogens here. Yoink, 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 yoink. What's going to be attracted not to my positive side of my water? Well, more what? Chloride. So I'd have a chloride maybe down here and a chloride over here and maybe some chlorides out here and chloride down here. And that's how my solution forms, where the positive side The positive side of my water surrounds my chlorides. Better surround this chloride, right? And the negative side of my water surrounds my sodiums. Good. And so that is what my final solution looks like. Now, here's the question. What has to happen for us to go from this situation to that situation? Well, first, let's take a look at my salt. What must happen here, first of all? Well, I've got an attraction between my sodiums and chlorides. Well, those must be separated somehow. So the first thing that has to happen is we have to overcome the attractive forces in the solute. Good. Now, quite often those attractive forces are IM forces. In this case, they are ionic forces. But in any case, the first step in forming a process is that we must overcome the attractive forces in the solute. Now note, I am not saying we're breaking bonds. I'm saying we are overcoming attractive forces. Next step, number 2. Well, what do I have to do? Well, I have my water molecules that are held together essentially, that are attracted to each other by hydrogen bonding. So I have to separate these. So I need to separate my water molecules. So what must happen? Number 2, we must overcome, once again, what? The attractive forces between solvent particles. Okay? Hey, I better go back and check something here. Let's go make sure. Not in, yoink, yoink, we got to be careful here. We have to overcome the attractive forces not in the solute, but I want to be clear about this. Not in, we're not talking about breaking the hydrogen from the oxygen if that were a solute. We want to overcome the attractive forces between solute particles. Let me be clear on that. Okay. In this case, it doesn't matter with salt, but we want to, if we have a molecular compound, we want to be clear. We are overcoming the IM forces, or we are overcoming the forces, the attractive forces between solute particles. Down here, we are overcoming the attractive forces between solvent particles. And let me make sure I clarify that clearly to you. That's a little redundant, isn't it? Clearly clarifying. If I am to clarify, that would be clear. Okay, here are my 2 waters. Here I have hydrogen bonding, right? But here I have what? And I should draw this better. There should be overlap, correct? Why is that? Because this is a covalent bond, right? The bond between my hydrogen and oxygen is covalent. Now, do I break this covalent bond when I form a solution? No. I do not break my covalent bonds. All I'm doing is overcoming my hydrogen bonding, and I'm separating one molecule from another. So I'm separating these guys, but I'm not pulling apart the hydrogens off the oxygen. So I'm not breaking, and that's the key, I am not breaking any bonds. No breaking of bonds here. I'm just overcoming attractive forces. Okay, so let's review again. Number 1, I overcome the attractive forces in the solute solute particles. Number 2, I overcome the attractive forces between solvent particles. And number 3, what happens? Well then, let's go back. I separate here, then what? Things come together down here, right? Good. And so what happens then? My solvent particles do what? My solvent particles are attracted to the solute particles and surround them. And that's how I make a solution. And this is important here. If I don't have any attraction between my solvent particles and solute particles, I am not going to form a solution. Okay, so those are the 3 steps. So let's go back and answer that question. Describe the process on a molecular scale. Okay, First of all, what's my solute? Well, it says calcium chloride. What's my solvent? It is implied when it says aqueous, because if it's aqueous, that means it is water, right? Good. So step one, the forces of attraction between calcium and chlorides are overcome. Good. Number two, the hydrogen bonding hydrogen bonding and what? Dipole and what? London between my water particles are overcome. Good. And then three, my water particles, in fact, what it is, it's going to be what? Let's be more specific. The positive side of my H2O is attracted to Cl minus and surround them. The negative side of H2O is attracted to what? To my calcium ions and they surround, right? And they surround them. There we go. And so that's the process. Cool. Is this solvation or hydration? Okay, so what is hydration? Let's go back to my beautiful drawing. Solvation is the process by which a solution forms in a subset of solvation. Let me see where can I draw this. Man, oh man, what a mess we've already created. And this is only day one. Look at all this. Phew. And hydration is a subset of solvation. Hydration is solvation in which water is the solvent. Yes. Okay, so if I have water as the solvent, the process is called hydration, not solvation. So back to our question. Is this solvation hydration? It's aqueous. That means water is my solvent. That means we have a situation of hydration. Woo! Cool. All right. You guys take a minute. You guys figure this one out, and I'll explain it when we come back. Well, first thing we understand is that we have a solution, yes. We have a solvent and a solute. Which is the solvent? Ethanol is the solvent. Water is the solute. So what's step one going to be? Step one is what? We want to overcome the IM forces between water molecules. And what are those IM forces? In this case, they are hydrogen bonding, dipole, and London forces, right? Good. Number two, we are going to overcome the IM forces or attractive forces between ethanol my ethanol molecules. By the way, what are those forces here? Well, I'm going to have London, of course. It is a dipole, so it's a polar molecule, so I'm going to have dipole, and look at that, folks. I have oxygen with an unshared pair on it with connected to a hydrogen, so we also have what? Hydrogen bonding. Just a review of IM forces. So we overcome the IM forces between my ethanol molecules. Let's write down that ethanol in case I've confused you with my beautiful picture. And then 3, what happens? The ethanol molecules now do what? They surround the water molecules. And if you were more specific, you would say what? The positive side of the ethanol surrounds the negative side of the water, and the negative side of the ethanol surrounds the positive side of the water molecules. Good. But that would be enough for me. Ethanol molecules now surround the water molecules. Boom. Now, is this solvation or hydration? Well, hydration means water is the solvent. Is water the solvent here? No. So this is not hydration. This is solvation. Okay. Let's see, where are we? I think it's a good time to quit. All right, see you next time.